But number one, is the one we just talked about, adiabatic. Right? No heat transfer. So in other words, Q is equal to 0, but there is work done. Now, it could be work done by the system or work done on the system. You can have adiabatic in both directions. Work done by the system, you have an increase in volume. Work done on the system, you have a decrease in volume. Right? Okay. Process number 2, isochoric. They don't necessarily have to be 1, 2. These are just 4 processes. I'm not necessarily numbering them with any kind of system here. But isochoric means that that's a process done at constant volume. So what that means is that the work is equal to 0, right? Because if I'm on my PV diagram and I don't change in volume, if I'm just going vertically up or vertically downwards on my PV diagram in terms of my process, then there's no area of the curve. Right? No area of the curve, there's no work. Neither positive nor negative. Right? Third is isobaric. And that's at, well, for isobaric, we have constant pressure, so that means that the work is just P times V2 minus V1. So we have constant pressure. And the last one is isothermal. So in that process, T is a constant. Okay, so on a PV diagram, what do these processes look like? So I'm going to start all of them at this point, up here on the upper left. And so the first process, the adiabatic process, looks something like this. So that's 1. I'm going to do all of these from either larger pressure to smaller pressure, or larger volume, smaller volume to larger volume. Okay. 2 is isochoric, that's at constant volume, so that's just a vertical process. So that would be 2. 3 is at constant pressure. So that would look like that. And then 4 is at constant temperature. And constant temperature would look something like this. Less steep than the adiabatic process. So the reason for numbering these is really so that I can label them in a PV diagram, not so much because they have some intrinsic numbers. So just out of curiosity, just to remind ourselves, which end of the adiabatic process, the one labeled 1, so the beginning or the end of that process has a higher temperature? It's the beginning. The one in the beginning has the higher temperature. Right, so this is going to be a lower temperature because on the PV diagram, if I go to higher pressure and higher volume, T is increasing. T increases in this direction, right? So everything along this line, along the isothermal process labeled 4, has the same temperature, right? So if T is increasing diagonally up and to the right, that means that this point at 1 is at a lower temperature than this process that's the isothermal process. Okay. All right. So the other thing too is that for adiabatic processes, in the ideal gas case only, we can find that the work is equal to
and CV times T2 minus T1 dt. All right, so heat engines. Heat engines go through a variety of combinations of thermodynamic processes. We're not going to go through all the sort of different cycles that you can have for heat engines. But what I want you to remember essentially about heat engines is that the efficiency of the heat engine is equal to the work that you get out of the heat engine divided by the heat that you remove from whatever hot temperature bath you have. Right? And we can also rewrite that as 1 plus QC, which is really the heat lost from the heat that you removed, divided by QH, the heat that you removed. Where the reason that this works, right, the reason that this is not going to give me an efficiency greater than 1, so this is efficiency. The reason that's not going to give me an efficiency greater than 1 is that QC is, one of these Q's is negative, right? So QC is typically negative, right? So in other words, we can also rewrite this as 1 minus the absolute value of QC over QH. And in terms of diagramming what's actually happening, right? So we have some heat bath up here, and we're removing some amount of QH from that heat bath, which is at TH. And that energy that's removed, some of it gets converted, or some of it goes into the cold reservoir. So the cold reservoir is down here at TC, and so some of that goes down there, and then whatever is remaining gets converted into work.
So that's schematically how we would draw a heat engine.
So this is our hot reservoir, and that's our cold reservoir. All right.
So that's one way that we can convert heat from some hot reservoir into work that we can then use. And one of the rules is, right, that we can never have 100% efficiency. We can never have an efficiency equal to 1, right? In whatever process we have, we cannot ever convert everything that we take out of the heat reservoir, the hot reservoir, into work, right? Some of it is always going to go to the cold reservoir. We're always going to lose a little bit. It's impossible to have a perfectly efficient process. Now, if we run things in reverse, we can get a refrigerator, which is certainly a nice reality to physics in the state of Florida. All right. And so, for a refrigerator, instead of an efficiency, we usually say we have a coefficient